Hey guys, today we are going to get into reaction rates, how quickly or how slowly chemical reactions take place. To start off, we have to have an idea of what a rate is. And there are a lot of common examples that we can use when we think about rates. When you consider a car that's moving, well, how quickly it goes from point A to point B, that is its rate of speed. Okay, we call that velocity. Uh, In this case, what we really want to think about is how quickly or how slowly chemicals change. They go from reactant into product. So in order for us to think about this, we have to have clearly defined units. And really the thing to focus on is it's a change in the number of moles that are present as reactants or as products. So typically, since it's common for us to use uh, aqueous solutions as we do these reactions, we can use molarity as our unit of the mole change. Okay, so it's the change in molarity over time. Now, when we say change in molarity over time, in the simplest form, that's moles per liter is our molarity, and then that's per unit of time, so per second. So we can actually show that unit with moles over liters over second. Okay, so or you could say molarity per second or moles per liter per second, and it's the same thing. Now, what we have to think about here is again this change that's happening can be expressed in a number of ways. But to try to help you understand this, I want to break it into different periods of time. So in the example that's shown here, you'll see that at time 0, all we have are these red particles. At time 20 seconds, we have fewer of the red particles and we now have blue particles. Then at time 40, you'll notice that you have even fewer of those red particles and even more of the blue. So we're changing from red to blue. That's one way of interpreting the change that we see here. Now, I'm going to give you a more specific example. We're going to talk about butyl chloride reacting in water. So here we have our chemical equation. Don't be distracted too much by the grouping of atoms. Really just focus on the change. Now, what we've done is we've taken the concentration values at different points in time, and we've recorded those concentrations. Then what we've done is we've determined the average rate between the first time and the second. So looking here between time 0 and time 5, we find concentrations go from 0.1 to 0.0905. When we calculate out a rate, the rate is shown at 1.9 times 10 to the negative fourth molarity per second. That is our change in molarity of our butyl chloride. Now, some things that we want to keep in mind here. The average rate can be calculated by looking at the change in our reactant, in this case butyl chloride, over a change in time. If you're given data points, what we need to do is write down those values. So we had our time final minus the initial would give us a change. And here we see that the final time would have been 50 seconds. The initial time was 0 seconds. For the molarities, we see that the final molarity, that we're going to call that M final, was our 0.0905 molar. So we take that value, subtract away the initial condition, which was our 0.1 molar. So doing the math on that, when we evaluate, we find 1.9 times 10 to the negative fourth power is the number of moles per liter per second, or the molarity per second, and that's our rate of change. Now, instantaneous rates are going to be used to give us the best approximation of the rate of a reaction. We consider the instantaneous rate because you'll notice that the rate is not constant here. We've got a curve. The rate changes over time. So given this curve, we want to approximate instantaneous rates. There are a couple ways of doing this. We say that this is the line tangent to a curve, the line tangent to a curve. What that means is if we would take a single point on that curve, there's a line that only touches on that one point. that line is the rate of change at that given time. So here at 600, our rate could be calculated by finding the slope of that line. Now, it's not always easy to do this. So there's a way that we tend to approximate this. What we could do is take a time frame and then go equidistant from that point to the left and right. So if I'm at time 300, I want to go up to time 200, and I'm going to go down to time 400 because I have points that are equidistant between them. And what I'm going to do is I'll draw a line from these 2 points, and you'll find that the slope of that line should approximately equal the slope of the tangent line. Now, knowing a rate and calculating a rate is important, but one of the most valuable things that we can do is we can look at the rate of one thing and compare it to another within a reaction. So this is stoichiometry. That's the heart of the concept here. So our rate, and this is going to be the general rate of the reaction, general rate is going to be equivalent to the loss of any reactant compared to the gain of any product when we have a reacting ratio that is 1 to 1, right? So in this case, again, we have our butyl chloride, and that reactant butyl chloride is changing in a 1 to 1 ratio. So we know that if our rate was -2 molarity per second for a reactant loss, that has to be equivalent to a +2 molarity per second for the product being gained. Now, if the ratio isn't 1 to 1, it muddles things up a little bit, but we can still figure this out by taking a look at the information. The coefficients are the key whenever we're doing stoichiometry. Here, you'll notice that we have 2 of our hydrogen iodide, we have 1 hydrogen gas, and we have 1 iodine gas present. When these react, we have a 2 to 1 to 1 ratio. So if I'm comparing the loss of hydrogen iodide to the formation of hydrogen gas, what we'll have to do is use those coefficients. Since hydrogen iodide is the starting thing, that's what I've been given, I want to cancel that. So I can do so breaking it down using a mole ratio. We divide away -2, which will also take care of the negative, the loss and loss cancel out, and we form +1 mole of hydrogen when that happens. So to give you a numerical example of this, if we began with -4 molarity per second, the mole ratio is going to cancel moles and go into moles. The molarities can be swapped just like moles. Our -4 molarity per second on the hydrogen iodide, I will cancel the moles of hydrogen iodide, and we found out again was -2, or a +1 moles of hydrogen. The math will be -4 divided -2 and times +1, which would give us a +2 molarity per second rate on hydrogen formation. Now let's consider some of the different factors that can affect a reaction rate. There are a variety of things that we can do if we wanted to speed up or slow down a reaction for various different purposes. The first thing is concentration. So recall that concentration is how much of a specific chemical is present in a specific volume, kind of like the density of a solution, that's concentration. If I were to increase the concentration, it means that I have more particles in that same space, and that means that you would increase the number of collisions. If you have more collisions, then more of those collisions can be successful, and our reaction rate will go up. So let's focus on that again. If I increase concentration, the molarity, I will increase the rate of our overall reaction. The next factor is pressure. So when we're talking about pressure, we're focused primarily on gas phase reactions. If I have a container, and in that container I have gas particles, well, again, we said they'll be colliding, they'll be bumping into each other, and if I increase the pressure in that container, it means that I have more collisions. Again, this is the idea with more collisions in that container. And more collisions means that we will have more successful reactions taking place. Now, if you're asking yourself, well, how do I increase pressure? One of the main ways you'll recall from Boyle's law is we can change pressure and volume in order to adjust the new pressure or volume. So if I were to take this container and I were to shrink it down to a smaller size, now I have the same number of particles in a smaller space. They collide more frequently, and that is your increase of pressure, leading to your increased rate. So when we look here, once again, you could, let's say, have a cylinder that contains this gas. If you press down on one end of the cylinder, it will shrink the volume, increasing the pressure. That's the main idea. So once again, an increase in pressure will give us an increase in the rate. Now our next factor is temperature. And I want you to recall that for temperature, don't think of it as hot or cold. That is not temperature. Temperature in an absolute sense is talking about energy. So if I increase temperature, what I'm doing is I'm increasing the kinetic energy in a sample. It means that the particles will move faster. So this Maxwell-Boltzmann distribution is what we call this. This shows you the distribution of particles under certain different temperature conditions. But I think it would actually kind of help if we visually saw this taking place. So let's take a peek at this animation. What we've done is we've taken two different particles. We have the blue particle, which is our lighter, faster particle, and we have a red particle, which is our slower particle, heavier. Okay. Now, under these conditions, you notice that the red particles are moving more slowly, which means they have a reduced kinetic energy, and the majority of those things are shown to the left. Okay, so our red is essentially representing our lower temperature distribution. Now the blue, these particles are representing our higher temperature distribution, and you'll notice that they have a much wider spread. Okay, so that increased spread, and now we've raised temperature, we've shifted that over. And you can see very, very clearly what's going on. As you raise temperature, the overall particles are going to shift to a higher kinetic energy. And what that means as an overall concept is more particles at high temperature have enough energy to successfully react. They cross the activation energy barrier. So once again, here's the main idea. If we increase the temperature, we will increase the rate of reaction. Next, we want to talk about particle size. When we have solids that are reacting, it's important that we understand that particle size is a factor. If I have large particles, only the outside edge of those particles is going to be available to react with some other reactant that's present in the solution. What this means is if we take the time to break this particle up, if I take a large crystal and I grind it with a mortar and pestle, let's say, then I'm able to expose more of the surface. And if more surface is exposed on this solid, then more collisions can exist. And again, collisions are the key here. The rate of reaction goes up with more collisions. So in this case, if I decrease the particle size, I will increase the rate of the chemical reaction. Now our final rate factor that we need to discuss is the introduction of a catalyst. So the concept of catalysis. A catalyst is a chemical that is not consumed in the process of a reaction, but it does interact with reactants in such a way that it makes a more efficient path for them to come together. So if I look at my traditional reaction pathway, well, what we see here is this is the time of reaction overall. On my y-axis, we have our chemical potential energy. And you'll notice that the reactant energy is higher than our product energy. So in this case, we have an exothermic reaction. In order for this reaction to take place, though, we have to remember that the collision has to have enough energy to reach what we call the activation energy. So the activation energy is the difference between our reactant potential energy and the potential energy of our activated complex. The reason that catalysts can speed a reaction up is because we find a more efficient path. What we've done here is we've modified the pathway so that I now have a reduced activation energy. The overall change in energy is unaffected, okay? So our delta H won't have any overall change, no overall impact. However, more particles that do collide will have enough energy to react. So once again, if I add a catalyst, we will increase the reaction rate. So to summarize these ideas, I have a video that I'm going to play. Just take a peek here. Hopefully this helps just bring these rate factors to bear for you.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has some more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing two particles together and orienting them correctly in space so that the two can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.